So, good morning, everyone. So, I'm going to talk about the challenges and solutions of developing a large-scale RAG application, specifically for a very specific and a niche area that is the legal domain. Let me just give you first an outline. I'll give you an example, a simple example in the RAG system, and then RAG applied to the legal domain. We'll talk about all the pipeline that goes into this, from data ingestion, management, consumption, and of course, how can we optimize this to serve the users that use the system, and then we'll dive a little bit on how to apply responsible AI into systems like this one. So this is a very simple RAG system, right? This is the basic example that is used throughout all the tutorials on the internet. So we have a user query, which is usually embedded. So we have an embedding, and we have some retrieval, and then we use this retrieval to ground the generation of the LLM alongside the query of the user in a textual form to have a contextualized output. So these give us, instead of using the internal knowledge of the large language model, we try to exploit the in-context learning of the prompt to just have the LLM answer based on those retrieved documents or files. So the legal domain is a very specific niche with very specific challenges. So, for example, we have multiple data sources, right? So we have legislation, we have court rules, we have regulatory entities, we have then private data from law firms, from legal departments that can grow from emails, memos, and so on, so on. Then we have this kind of mention from one document to the other, right? So for example, court rules most of the time mention law, and we want to have that link when we are developing such systems. So we want to have this ability to have cross-information. Then we also have data hierarchy, right? So there are some laws that are more important than others. There are also some court rules that are more important than others. For example, the Supreme Court rules normally are the top of the hierarchy. Then we also have the European courts, etc., etc. And another challenge that is very, very important for this specific domain is the freshness of your data. So basically, you want to guarantee that everything that's ingested or that is stored in the most updated version possible, right? So we don't have a lawyer generating a memo or an email to a client and having a law that is outdated or a subject that is completely outdated. So what we want to do with Affine is build a system that guarantees that the generation is grounded on real data, on court rules, laws, private data from these departments. And of course, we want to have grounded references because our users, in particular legal domain, are very critical, and they want to know where this information comes from. Is it correct? Should I use it to produce a memo, something like that? And of course, with this, there's less risk of hallucination and less risk overall for the business and the courts and some other topics of interest for the legal domain. So one thing that when we started building this, we realized is that when you are building a RAG application, you just don't want to build or at least optimize the generation part. One of the most important things that you want to focus is on search, so building a great search engine. There's a great article from Elicit, which is a startup developing an AI research assistant, that's this build a search engine, not a vector database. I invite you all to scan the QR code and read it later. But the main idea is this, is if you want to build a RAG-based tool, first build search. And building a search engine is not easy. There are several and multiple challenges along the way, from ingestion, management, consumption, and then optimization. And I'm gonna touch in each one of these pillars and talk a little bit about this. So first, let's talk about data ingestion. As I said, there are a lot of data sources, right? Some public, some private. There are a lot of structure in this data, a lot of different structure. For example, legislation and court rules, they usually come from websites on the internet, so HTML, XML, and JSON. Regulatory entities are usually PDFs, blog posts and articles are usually also HTML, but then we have cloud storage and user uploads that can be a little bit of everything. So PDFs, Excel files, doc, Word files, even emails. So there's a lot of homogeneity heterogeneity here, and then we go to the next step of the ingestion pipeline, which is data transformation, right? So we need to parse all these different types of data. We can do metadata extraction, we can do chunking if we're doing semantic search, then embedding. We can also do some summarization and some name entity recognition, stuff like this. Then if we have, we have to store our data, so we have a document store for that. We also have to store our vectors if we are doing semantic search, and if we want to do some more advanced stuff, like for example citation graphs or entity graphs, we can also do graph storing. So this is an example of our usual data pipeline. And this is something that I also want you to focus a little bit, and if there's something that I want you to leave from this talk is that data quality is really, really important. So any LLM app is only good as the data you feed. So if you feed them garbage in, garbage out. You know the deal. So we have several types of data. Usually we have a parser, something that can destructure this data into more of a structured format. Usually it's a JSON object, which can have content. This content can be divided in sections, for example. Then we can extract metadata, such as dates, authors, the source where it came from, stuff like that. And then we can also have a post-processing step, where we can do summarization, chunking, named entity recognition, and then we can save it to data store. So this is the step where we can clean our data and have an actually structure to it. Now, of course, as I said, each source has its own challenges, but a good parsing, so clean data, improves overall performance of our search engine. And we actually tried and experimented several of these strategies that we have here. For example, for semi-structured data, we can use the generic Knife parsers that you can find in libraries like Llama Index or LangChain. You can use tailored or tailored build parsers that basically you code for yourself, depending on the source, or you can use LLMs. For example, ask an LLM to transform an HTML into Markdown or a JSON, stuff like that. So for example, for this example here, this is a law from the Portuguese legislation. This is a website. And what we did, we created a tailored parser that transforms this HTML in this JSON. So everything, it's parsed, the typing is perfect for use for indexing and for querying. We can also have some doc types. In this case, this is a law. We could also have a law decree, stuff like that. We have the original link to the PDF if we want to show our users, and so on, so on, so on. And then we also have sections. Basically, this is the content, but instead of being just a a big blob of text, it's parsed along these sections and along these articles. This way, we can, for example, reference to the user. Oh, so this answer was based on this piece of text that was found on this article that was on this page. We can also have a post-processing step to generate an AI summary that you can see here. So there's a lot of things that you can do, but the main idea here that I want to pass is the better the data is treated and cleaned, the better will be the responses of your search engine. Then, of course, we'll have file data. And file data is kind of like the jungle, right? You can have Words, PDFs, Excels, and then these, for example, for PDFs, the layouts can be multiple. So you can have double columns, you can have footnotes, paragraphs, you can have floating images alongside the file, the document, and we also started with generic and naive parsers, also with the OCR. But what we found out is that they sucked. They sucked very, very much. And when we tried to do RAG over these documents, the answers were kind of like garbage. So what we started doing was developing these document intelligence models, basically doing layout understanding and extracting information from these files using these based on these models. So Layout LM from Microsoft, also Donut, I think is from Microsoft, and YOLO. And this works pretty well. You don't need big GPUs to fine-tune them, and they give you pretty good results. So, and now there's also a new trend. When we started doing this, visual large language models were not a thing. Now they kind of are, and they also are pretty good, but they are pretty big, so they are pretty expensive. But they can help you extract also information from these type of files. So let me talk a little bit about chunking, because this is something that I think everyone who had experience working with RAG, with Retrieval Augmented Generation, passed through. That's basically, there are some challenges with chunking, right? So you want, when you're chunking a piece of text, you want to maintain text structure. You don't want to just collapse the text in sections that don't make sense. You want to have a good text structure. You also have to guarantee that that piece of text fits the embedding model for semantic retrieval, and you also have to understand what type of queries your user is trying to do, if that makes sense for those chunk strategies. So a good chunk strategy is needed to do all this. So maintaining the local context and the global context of each chunk. And with this will enhance the quality of your retrieval, and also it also depends the size of the embedding, right? For example, the original OpenAI embeddings, they had over 1,000 dimensions. And for example, our system, Affine, right now we have around 5 million documents. You multiply that by, I don't know, some 30 chunks per document, so you can see this scaling. So if you have a vector database with vectors with over 1,000 dimensions, and if you try to query them in the order of the millions, this will be very, very slow, and the costs will also be very high because you have to keep all those vectors in memory. So you would end up with a machine with like 200 gigabytes of RAM. So just a little bit of note on post-processing. These are some things that we tried and did. So summarization, you can do abstractive or extractive. Extractive is much more cheaper, but it's not usually very effective. So abstractive summarization captures the global context of the document. We usually use LLMs to do this. You can also do metadata extraction for filtering. This is something that I'll talk a little bit in a minute, but it's very, very important. You can use name entity recognition to create a graph, so you can query to do, for example, library search. Embedding, we talked about it, and of course, document indexing. You can also apply keyword search, lexical search, for example, for a BM25 algorithm. Now, let's talk a little bit about data management. The legal domain, it's also special in this topic because every day new data is available in these new official sources or regulatory entities. New legislation, court rules are coming out every day, so we need to keep the freshness of our system. And then court rules affect past court rule decisions, and legislation can update or take down previous laws. So this is a big challenge to have a system always updated for this. And these updates are usually in a form of expression, right? So, for example, this law revokes that article from that law, these court rules nullifies the decision made previously, blah, 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 blah. And this is sometimes tough to extract from these documents. What we do much of the time is use rule-based models, so regex or bag of words, and for the more tough cases, we use LLMs. So basically, for example, your example in the right. So we have a cron worker every day pinging these sources for new information, for public data. We ingest those news documents, and well, we insert the new document in our stores, and then we try to extract updates. And if we identify any new updates, we update the existing documents already in our document stores. This is easier because we basically, when we insert a new document, it gets it's well structured in JSON, so we can extract updates from specific fields and update them on our document store. Of course, with this, we have a challenge, a big challenge in terms of infrastructure. We have storage that keeps growing. We have to, of course, have in mind data redundancy and backups, the compute for doing basically all these and all the post-processing, the scalability of each source. As I said, the semantic one, the vector store, it's I think in terms of compute and scalability, it's the most challenging one because more vectors, more in-memory storage, more latency, more costs, as I said here. And another one that people don't talk much about is this signal-to-noise ratio. So when you start increasing your vector space, when you're trying to do search in a vector space, the query that the user does when you're trying, so in the embedding, the query, it doesn't have much of a contextual information, right? So the semantic meaning of the query, it's not very rich. So when you try to do a semantic search in a very big, so in order of the millions, in a vector space, the signal-to-noise ratio, it's very low. So you will get, when you retrieve documents, you'll get documents that the idea of the query in the document is there, but that was not what the user asked for. So you have a lot of garbage on those result sets that you get. But in terms of strategies, what we end up doing is basically have a vector store or search engines that can be sharded and distributed, have caching mechanisms, for example, for queries, do vector quantization on your vector stores and on your embeddings when you're doing user embedding. Use materialistic embeddings. This is, I think, now the standard for the latest embeddings, for example, for OpenAI, and of course, parallel everything. So for example, for the cron workers and stuff like this, all this compute, everything that's not dependent on previous steps in the pipeline, just parallelize everything. Now, let's talk a little bit about data consumption. When you're building a search engine, you just don't want to basically do things in a blind way, right? So you want to understand what the user wants. You want to understand his intent or their intent. So they want to find documents, and this is especially important in RAG systems, because sometimes when a user wants something in the RAG system, can be a question answering, can be, hey, find me these documents. So there are lots of different use cases. And understanding intent is very important for this. And extracting metadata for these kind of use cases, it's very effective because, for example, using GPT functions, for example, with the question that I have here, was there any new legislation about stock options introduced in 2024? We can extract filters, like, for example, source. I just want to look for legislation. I don't want to look for court rules. I don't want to look for internal emails. I just want to look for legislation. So we can increase the signal-to-noise ratio, the thing that I was talking about previously, because we are searching in smaller sets. Now, the query is just stock options. I just want legislation about stock options in the year of 2024, and I want a document. I don't want to do question answering. I just want a document. Now, of course, we are talking about RAG, so we talked about search, retrieval. Let me talk a little bit about generation. So this is something that's also the new generation of LLMs kind of try to tackle all these challenges. So from the release of ChatGPT, the context length increased so much. We don't have the issue, or at least it's minimized the issue of the needle in the haystack. So basically, you don't really care the order of the documents that you pass to the prompt. If the documents are relevant, the reasoning, and I'm reasoning with air quotes, of the large language model can be effective to at least identify what parts of our prompt would answer to our user query, but there are some challenges that are still very, very important, and for the legal domain, it's very important for us to tackle it. That's handling contradictory information, because as I said, sometimes previous documents said one thing, the law is updated, and new documents would say another. So we need to handle contradictory information. We need also to balance details and conciseness. For example, a lawyer wants to create a summary of a document. Okay, but what do you want? What key points do you want to maintain? What do you want to extract from that document? This is very important. Of course, we also have different LLM prompt templates. Here is a prompt template that's usually used in Claude from Anthropic. Usually, GPT-4 and the most advanced LLMs can also do reasoning with these, but some are optimized better than the others, so you have to also take care of this, and of course, dealing with outdated and incorrect data. We prefer to do this in our search engine, so we don't want to risk sending this to the LLM. Okay, so basically, now that we have this search engine, we can do a lot of cool things, right? So we can do simple RAG. So in terms of orchestration, we can do just simple RAG, the example that I showed you in the beginning. We can do AI agents. So basically, each part of our RAG system, for example, the graph store, the vector store, the document store, the BM25 index, can be tools. And we can have agents planning and use those tools to create complex workflows. And we can also, if we don't want to have an agent tailor a plan, we can also create already tailor-made workflows. And this then can have several applications, QA on legislation, court rule analysis, contract review, compliance review, legal research, regulatory navigation, so on, so on. So now that we build a search engine on top of this legal data, we can have a lot of cool applications. Okay, so let me now enter here a section that's important for me. We are part of the Center for Responsible AI, and one of the things that's very important, and we are dealing with the legal domain, we have to take some responsibility. So usually there are several pillars in responsible AI. These can be interchangeable, but the top four is privacy, fairness, reliability, and explainability. For this talk, I'm going to speak a little bit of privacy and explainability. And in terms of explainability, usually reg systems have this system for references and citations. And you can do this in several ways. Some have advantages, some have disadvantages. If you're using a closed source model, you have two options. Or you use the LLM to generate the citations, so they are generated on the fly and they are dependent on the model accuracy, or you do fuzzy matching with the documents that you found out from your search engine. But this is not very good. So the threshold is configurable, but it's tolerant to minor errors. But if you use part of the sentence and then you start kind of paraphrasing it, this will completely fail. And there are some, if you are using an open source model, you can do attention-based. So basically, you create a metric based on the attention weight of the open source models that you can highlight the tokens that were used to generate that part of the answer. And there's also some cool work on interpretable weights or interpretable features. There's a cool blog post about this. So basically, what you do, you train autoencoder, sparse autoencoder, to understand what semantic ideas are activated when you generate a response. So for example, this is a very simple example, basically because so this is our document, and this is the answer that was generated. So here we have the citations, and here we can see that the part that was used to generate this one was this one over here, but this one is very simple because it's the literal phrase, right? So, but this is the idea, so explainability. So, for example, a lawyer could check this answer. Oh, there's a reference here. He could click, he could go to there, and he would have an highlight part to understand what generated this response. So, in terms of privacy, when we started developing Affine, we wanted to have privacy by design, right? So there are lots of enterprise requirements with data confidentiality, regulatory compliance, access control, audits, stuff like that. So we started doing this by design. So basically, all our client data is in silos, or silos. We allow VPC installation, so everything that I've talked about can be installed on our clients' virtual private clouds with end-to-end encryption, auth policies in the application layer, and of course, federated search. So basically, federated search here is used to query public sources and then query private sources and then fuse them together. So we don't have to have all our public data stored in our client's VPC. And of course, with this, the value of private data is very important because legal departments, law firms, they've produced very rich data, very rich private data over the years, but a bunch of this data is not used, and by using Affine, we allow them to use this data and to take value from it. And of course, this is a very competitive advantage. So let me talk a little bit about optimization. when you're trying to build a search engine or a RAG system, the first thing you want to do is get a benchmark. This is the most important thing you want to do. Get a benchmark, create a representative test set, define an evaluation criteria. I have some examples here. For example, for search, you have the classic precision and recall, you have the mean reciprocal rank, and you have the normalized discount gain. So the difference between these on the top and on the bottom is basically the order here matters. So relevant documents are there, but there are documents that are more relevant than the others. If this is your case, use these two. If not, you can just use recall if you want to just understand if the relevant documents are being fetched from the search engine. And of course, a metrics for generation, this is more for answer. So in terms of faithfulness, coherence, relevance, correctness, the hallucination rate, this is very important, and this is very hard to estimate. And of course, human feedback. If you're working with end users, you can do stuff like A/B testing or even the classic thumbs up, thumbs down to understand if the things that you deploy to production are actually working. And start with a simple baseline. BM25 as your baseline comparison, then build on top of it. Okay, so basically search optimization, I think it's the big thing when you're developing a search engine to do. So try different search strategies or algorithms, keywords. You can play around with the thresholds from BM25. Lemmatization and tokenization are very important in terms of language. For example, the tokenization and lemmatization for English is completely different from Portuguese, and this is something that we noticed, is that when we started mixing the two, things started to break. The results were not so good because of this. So make sure that you are using tokenizers and lemmatizers specifically for the language that you are using. And of course, semantic, choose a good embedding model. Right now, there are embedding models that are being specific for the domain that you're working. There are embedding models for finance, for law, and you can also use the general ones from Google or from OpenAI. The embedding size in terms of scale, and of course, the chunk strategy is also very important if you want to maintain that coherence. And of course, the graph, if you want to extract entities and their relationships, and what entities are those, what relationships do you want to extract, and the transversal algorithm. How can I look in the graph what I want to find? For example, if I extract an entity from my user query, what I want to find. I want to do community finding. I just want to transverse the graph and find their neighbors, stuff like that. Of course, when we talk about combining search strategies, we have to talk about fusion. Fusion is a technique to combine different result sets from different search strategy. For example, the BM25, the score from the result set is usually unbounded, but the semantic is usually bounded to 1 and 0 if you're using cosine similarity. So how do we combine these different search algorithms? Well, there are some fusion strategies. The most used ones are relative score fusion and reciprocal score fusion. You can test them and see which one works better. Again, use the benchmark for this. Linear normalization is just a greedy way to do it. From our experience, it never kind of works. So yeah, focus on these two. Okay, so remember that in the beginning, I said that the user query usually it doesn't have a very rich semantic meaning. So there are some strategies by using LLMs to kind of enrich the semantic meaning of the user query. So in this first example here, we can use the query, and this is something, for example, that Perplexity does, that you can have the user query and rewrite or paraphrase that query in multiple ones, and then you can do semantic search over the multiple queries that was generated, and then you you create a result set with all the results from this query. Another thing that's also very used in, for example, Llama Index and LangChain is height, that basically you kind of have a query and you ask the LLM to create a document that, okay, so for example, create me a document that would correspond to this user query, passage, a law, for example, stuff like that. Then we use the document, we embed the document and use the embedding of the document, of the generated document, to do the semantic retrieval. Another thing that we can do is basically use a strategy of divide and conquer, that basically we have a query and we kind of create subqueries, so basically planning follow-up questions or really just dividing the problems in sub-problems, and then we try to answer each one, and then we fuse the results in the end. And this one is something that's kind of new, that's using these new splayed models. These are bi-encoder models that basically, encoder-only models, that what they do is that from a semantic query, for example, a question, you generate additional keywords, and then you use a lexical search engine, for example, BM25, to search these additional keywords with Boolean operators, for example, or ands, and then you fuse these results with the classic search strategies. This has been pretty important because it has a lot of impact, because sometimes the semantic meaning, as I said, for very big vector spaces can have can be really noisy. But when you do keyword search, it isn't that so much. So you can use this. So of course, there are a lot of other methods. You can do re-ranking models if you want to rank important documents at the top. This can be used with encoder-only models. You can also use LLMs, question an LLM, is this document relevant for my use case? Of course, that's very expensive and very slow. So if you want to improve recall, there are also some easy to implement and very effective techniques called property boosting. This is something I think from Elasticsearch, but basically some data properties are more important than others. So for example, in case of law, we want to have very big importance to the date of the document. So if that document it's relevant, is it more relevant than a new document that came last week? Maybe. Use the benchmark to evaluate this. And of course, there are more advanced RAG strategies, multi-op, retrieve, for example, document summaries, answer on chunks, and agentic RAG. So I think just to finalize, the idea that I want you to leave is this one. If you want to build a RAG-based tool, first build search and read that article at the beginning. I think this is the most important thing. But yeah, so when developing domain-specific RAG applications, collect a benchmark. We collected our benchmark from our partners. They are basically legal professionals. They knew what they were doing. So basically, we have a very specific benchmark for our domain and optimize for search first. Understand how your data is structured. So develop parsers to clean your data. Develop processing methods for data enrichment. Understand how the users use your system. This is also very important. This allows you to reduce the noise and to give them better results. And of course, if after this, test more advanced methods, more search strategies, fusion, query expansion, agents. So start small, experiment a lot, and implement these more advanced methods at the end. Yeah, so that was it. Thank you so much.